So good morning. We continue with our discussions on analysis on R. We were considering in the last few lectures the algebraic structure of R. That means Rn looked at as a linear space with the usual addition and scalar multiplication. Now what we want to do is we want to bring in an additional structure on that through what is called the distance notion, or since we are working with vectors, by introducing the concept of length for the vectors. Now this is our idea. Now later on, we begin with what is called our usual standard notion of the length of a vector to begin with, and that leads to what is called the Euclidean structure of R. And then of course you see that there are various generalizations of this leading to unusual notions of length and distance that you can introduce on this space. But that we may make a remark in the passing, but will not be bothered about it right now in detail. Okay. So what is that you have? Let us write down the essentials that we have already seen. So we are in Rn, so we fix the notations. X we define as the order n tuple. Y we set as y1. Where xi, yi are of course real numbers. Then we have the sum of these two vectors defined as the sum, and scalar multiple alpha x defined as alpha x1 alpha belonging to 1. Now with this addition and scalar multiplication, Rn is a vector space over R. And its of dimension these informations we already have. Now we introduce two structures, two expressions. One is called the length of the vector, the other one is called the dot product. Or let me just write down the dot product. So the dot product or later we will see this as this is the prelude to introducing what are called inner products on vector spaces and talking about inner product spaces, Hilbert spaces and so on. So is defined by if you look at it, this is dot product is essentially a map from Rn cross Rn to R. So this is from, so the dot product or is a map from it is a bilinear. Bilinear means, you see, it's something like this. Suppose I denote x dot y or x comma y is mapped to x dot y. This is bilinear because you have two variables x and y. It is linear in the first variable and also linear in the second variable. Okay. Then you also have, so this is bilinear. Since we are working only on R and Rn, see the complexification, it does not come into the picture for. So we are talking about a bilinear map. It's bilinear map, that is linear in the first variable as well as maybe the second variable. That means x1 plus x2 is mapped to x1 dot y plus x2 dot y. Alpha x comma y is mapped to alpha times x dot y. Similarly, x comma, see, very funny. So here x, y are, so x1, x2, y1, y2, x, y are alpha belongs to. That means if you take the dot product of x1 plus x2, this map is defined by this close to this. Therefore, so in short, this means that x1 plus x2 dot y equal to dot y plus x2. That's the meaning. And similarly for this and so on. So you can write it down. So it will be clear. And this is the definition which you have to use and then check everything, and this just routine bulwark that you have to do. Now we also introduce a notation of Euclidean norm, defined as half, and this is equal to sigma this is the square root of x dot x. Now all these are of course generalized from our experience of working in R2 and R3. Okay. Now let us explore this on R2. R2. You have x dot y equal to x1 y1 plus y2. What does this give? See, you observe that, okay, what is this actually? So you have two vectors. If you work this out, you can easily prove that if this angle is theta. Okay? You see that x1 y1 plus x2 y2 divided by this is simple to verify, but easy. Okay. So this can be rewritten as x dot y divided by now you see that in R3 also the same formula works. Okay, the same. Because what you have is this one, x dot y equal to sigma I equal to 1 to 3 xi yi norm of x that is the length of the vector. These are all straightforward from the Cartesian coordinate representation, and applying Pythagoras theorem you get this length of the vector, and this is And you also observe that the dot product has the property that x dot y is you can go. Oh, that's very easy. Okay. So x dot y is a real number. Okay. And then x dot x is a non-negative real number. X dot x is equal to 0 if and only if x equal to 0, and that's another property that you can define. Okay, and so on. Okay, so all these properties I listed out. Okay, so we have now the concept of inner product and then the concept of length of a set. So this is a length derived from an inner product. So it gives two things. One, it talks about the length of the vector. It also talks about the angle between the two vectors. So the dot product at the same time does two things, namely talks about the, and of course you can see that norm of x2 that I think we have already said, norm of is greater than or equal to 0. Put a 2 here for designating or indicating that it's the Euclidean length that you are talking about. Okay? And then you see that x dot y equal to y dot x. X dot y is a bilinear function from R cross Okay, now this is what is called symmetry. Of course, if you are considering a complex space, then of course you will have to bring in some changes, which we shall not bother right now because we are working in R. So we confine ourselves to R. Okay. Now let us put some of these results in the form of a theorem. I leave it to you to prove these results. For x, y, z, Rn, and alpha belonging to R, we have the following properties. The first property is that equal to 0. The second property is equal to 0. The third property is norm of alpha x2, and then we have the fourth property, x dot y absolute value is less than or equal to norm of x, norm of y. Now this is somewhat non-trivial. And then the fifth property, norm of this is the triangular inequality that you have. Okay. Now we look at this. So this is the same of 6. Okay. Now some of these are very trivial to verify. Just go to the definition and verify it. Okay. So 1, 2, 3 are trivial. If you look at the fourth one is a very fascinating one. This is called the Schwarz inequality. 4 is called the Schwarz inequality. Schwarz's inequality. And interestingly, it's also called a Cauchy-Schwarz inequality or Schwarz inequality, short form. Or even the Soviet, in the heydays of Soviet Union, they were also telling that this is called Cauchy, Schwarz, Bunyakovsky inequality. Or Cauchy-Bunyakovsky inequality. I mean, you know, like it goes with some name of some Soviet mathematician, and they used to take pride in saying that this was independently done by Bunyakovsky. Okay, that's just something very interesting from the literature. Okay, but anyway, it doesn't matter what name it comes. But if you carefully look at this, what is this? This, if you take R2, this means the following. Okay, in R2, x dot y is x1, y1 plus x2, y2. And you have the formula which I think you should prove. It's very easy to prove from first principles that x1 y1 plus x2 y2 divided by x1 square plus x2 square to the power half, y1 square plus y2 to the power half, I should write here. This is equal to cos theta. That is simple. So, yeah. Now you see that this is it tells something. You know that cos theta lies between -1 and +1, or you have mod cos theta, or any theta is less than or equal to 1. And theta is the angle between the two vectors x1, x2 and y1, y2. It's quite easy to prove. You can put it in the polar form, these two things, and then just take the x1, y1 plus x2, y2, and then divide by the length, and the length will be r1, r2, etc., etc. So it's very easy to prove. Okay, right. But the important thing is that mod cos theta is less than or equal to 1. And if you just use this, then it follows that mod x1 y1 plus x2 y2 is less than or equal to norm of x2. So this is an offshoot. Likewise, in R3 also you can prove this independently. It's not verification. This is how mathematics grows. Your experience on R2, your experience on R3. Now you immediately see that it's very, very lucidly it gets carried over to RL. Okay, of course there are very strong reasons to talk about n-dimensional spaces coming from other areas of mathematics. Okay, but certainly you are going to be totally disconnected from your visual perception of such spaces. You will have to work analytically. Okay, because you cannot have a geometric image of Rn for n greater than or equal to 4. Okay, because we live in a 3-dimensional world, and that's unfortunate. Okay. Also, there is the 4th dimension of time along with it, space and time together, but that's not something very visible. You keep drifting from one 3-dimensional space into another 3-dimensional space as time elapses. But in R3, because you are very comfortable. In R2 you are very comfortable. In R you are very comfortable. So all these things are very comfortable. But beyond that, there is no such geometric image. Therefore, what you do, what you mean by cos theta, all these have no meaning. So you have to define, in that case, cos theta as x dot y divided by norm of x into norm of y. This is just taking a generalization, going for a generalization. But the more right thing is, you see that whether this particular inequality will be valid or not. So the question that you are asking is this: x dot y this is the question that you are asking. Is this really true? Okay. So the question mark here, we have to go for it. Well, it's not trivial. So one has to prove from the basis. Okay. What one does is this. Okay. See, okay, right. So we consider the vector lambda y, x minus lambda y, where lambda belongs to right? Now you know that straight away from the property 1, you know that the 0 is less than or equal to norm of whole square. And this, you know, this is equal to x minus lambda y dot x minus lambda y. It's the dot product of these two. Now it's easy to compute it. Make some computations here. Now this is equal to square x dot x and minus 2 x dot y divided by minus twice lambda y plus lambda square very easy to work out. Now we assume y equal to 0. Then what happens? Look at our inequality. This is the inequality that we want. You see that x dot y is, in that case, this is equal to 0, and norm y 2 is also equal to 0, which implies the given so when y equal to 0, the given inequality is holds. Okay, now we take, so now assume not equal to 0. If y is not equal to 0, now we take lambda in a particular way. So choose lambda equal to, choose lambda equal to x dot y divided by norm of square. Choose this. Then you go ahead with the computation. Then what do you get? Then we have 0 is less than or equal to norm of square minus twice x dot y whole square divided by whole square plus this is after simplicity. We just multiply, take lambda square and then cancel out this y is not equal to 0, therefore we do this, and this gives So from this you can easily get that is true for any choice of x, symmetry. Okay. Right? Therefore, this is true when y equal to 0, when y not equal to 0, also it is true. Therefore, hence, Schwarz's inequality now this proof is quite something which can be generalized even to when you go to infinite dimensional spaces or anything. It's a very nice way of proving it without the sorting to the component form and then messing up with all the computations and so on. Now this is very simple. Right. So we have proved this. Right? And lambda equal to x dot y divided by norm y2 square is a very legitimate choice for lambda because it's a scalar. I mean, lambda is any real number, this is true, and this is well defined. So that's a proof for this inequality. Now, one of the immediate consequences of this is the following inequality. That is, we have now we prove that now this phi is an immediate consequence of how it comes is this. If you take norm of this is equal to x plus y dot y, and this if you compute good notations help you to work through the proofs without complications. Okay. Now this is equal to y you are applying Cauchy's inequality here, so you get modulus of this is less than or equal to norm of x 2 into norm of y 2 plus norm of square by Schwarz. Inequality. And this you know is equal to okay. So that proves it. Okay. Because of this inequality, everything. Right? Therefore, the norm criteria, namely that is norm of so, well, in a way this is the following, that is, this is the vector x, this is the vector y, and you see that your addition rule is parallelogram law. This is your x plus y. What it says is that the length of, because it's parallelogram law, it is, these two sides are added and then resolved. Okay, you see. So this side, the length of this side is equal to the length of this side. So norm of the length of x plus y is less than or equal to the length of x plus the length of this triangular vector. Okay. So this is the meaning of it. Okay. So this is actually length of and if you just scan through the proof of this, now you see that you can show that this is equal true, that equality holds that means x and y are along the same direction. That is the vectors along the same line. I think I would better put it along the same line. Because it could be also in the negative direction. The lambda could be both positive and then also this is. So that is very easy to prove. You don't need much work to observe that. Okay, fine. So let me just come back and make some remark on this. Now you see that if you take the two vectors, we have already seen that we are talking about the dot product talks about the angle between the two vectors, and you see that the cos theta is computed in terms of x dot y, norm of x and norm of y. What the Cauchy-Schwarz inequality says is that modulus of cos theta is less than or equal to 1. Now this is generalized into the higher dimensions, and in the higher dimensions you are able to prove independently without going to the cos theta. Therefore, that property is carried through into the n-dimensional spaces, and later you can also see that in any inner product space this is true, whether it is finite dimensional or infinite dimensional. This particular inequality plays a very crucial role in the study of what are called inner product spaces. Okay, so just make that remark. But what you should observe is that the role of R2 and R3 in understanding the problem. Okay? So we have the geometric insight into the structure of R2 and R3. From that, lot of things can be read out. When you generalize, you don't have that vision. But then your experience of working on R2 and R3 can be carried through, or a lot of results can be expected to be true, which is normally valid in R2 and R3. Now this is one way of really developing mathematics, and that is something that you should really observe, and this is very important. That is why it's not that you prove in the all generality something, but you should also look at what exactly you are doing on very handy examples. I am not taking R. R is also a good model for this, but R is probably too non-visible to see many of these things. Okay? For obvious reasons. But R2 turns out to be a very credible model, and R3 also. R2 you can draw pictures on a plane, on the on a sheet of paper or on the board. But R3 probably you can, if you are an artist, you can just draw the pictures and get a good perception of what is going on. But certainly you can do nothing with R. You cannot draw pictures of R. Okay, right? But then your task is this: anticipate results that are valid in the general scenario by looking at or capturing your experience of working with examples where you can visualize this. And this is very crucial in the study of linear spaces, because always every result, I would suggest that if you are working in a linear space, even sometimes in the case of infinite dimensional spaces, you should go down to R2 and R3 and see what that particular result means. Because the dimension being finite is a handicap when you work in infinite dimensional spaces. Not all the results that you see valid on finite dimensional spaces need be true in an infinite dimensional space. So one has to be cautious. But nevertheless, you will get a lot of insight into the working of the results that you can expect there. Okay. Therefore, a thorough analysis, and every time visiting R2 and R3 with your theorems will give you a lot of insight into the statement of the theorems. Now, I would even say that in the first reading of any new material, you should ignore the proof of theorems and take them for granted. But what you should do is go for the definitions, try to understand them on fairly simple but non-trivial examples. Secondly, so also you see what the statement of the theorem is, distinguish between what are the conditions stated and the conclusions, and see what it means on fairly simple non-trivial examples, and then get a feeling for these results. And after you get the feeling, then you understand the basic questions behind the result or which leads to the particular theorem, you should actually go to work out the proof. Quite often what happens is you will be able to work out the proof on your own. If you are sharp enough, you should close the book and then try to figure through the proof. That means from the given data, how to reach from the given data to the conclusion. This you will be able to work out in it. You have a lot of advantage when you work in R2 and R3 because you have a lot of visual pictures available what goes on. And this is very important, extremely important. Okay? Yeah. So with that little sermon, now we go further. Now see, that is more or less the basic things that are on Rn. I also introduced one more thing. I define d2 of xy defined as norm of now if you look at the sixth statement, the sixth statement can be written in terms of d2. The sixth statement is rewritten as d2 of now you see this is called the metric. So the norm induces a metric distance. In Rn, and let us see, let's prove that this is a distance actually. What are the basic properties of the distance? Okay, let us take R. We say that D is a distance. The following is true. D is a map from R with the following properties. That so D of is in fact is a real number, and more specifically you can write this as R plus union 0. That means this is greater than or. Then that's the first thing. So second property is d of x is equal to 0, and d of equal to 0 you can only use x equal to that. That means d of xy equal to 0 if and only if x equal to y. The third property is that d of xy is equal to that means the distance from A to B is the same as the distance from B to A. Then the fourth property is that distance from x to y, x to z is less than or equal to distance from x to y plus distance from y to z. That means if you travel from x to z, then the distance you have to travel is certainly less than or equal to the direct distance. It is less than or equal to the distance you have to travel if you were to route or travel through a point z, sorry, a point y. This is the distance from x to y plus the distance from y to z. This is the triangular inequality, which says that in a space distance from x to z okay. This is a triangular inequality. So these are the basic properties of a distance function. So distance function is defined from Rn cross Rn. In fact, any function satisfying these four properties will be called a distance. It's a legitimate distance and it is given a name called metric. Okay. So a space with a metric is what you call a metric space. Right? And there is more structure on Rn because Rn is also a normed linear space. In fact, every normed linear space is a metric space. Okay, so you see that now this is root, right? Rn now there are exotic norms that you can introduce. There are exotic metrics that you can introduce on spaces, and it is not that every metric comes out of a norm. Only if you are in a linear space, there is sense to talk about a norm. Okay. Only if you are in a normed linear space you can talk about it, or a linear space you can talk about it, because all the conditions that you list out uses heavily the structure of linear spacing, because you should be in a position to talk about x plus y, you should be in a position to talk about lambda x and so on, which is not required when you talk about a metric space. In a metric space, all that you need is, if x is a set of objects, and then you define a map from x cross x to R plus union 0, satisfying these properties, then it's a metric space. And it doesn't talk about the length of an element or any such thing, which may not be possible to introduce that. So there are very exotic metric that you can introduce without using the norm. So every normed linear space is a every normed linear space but I think it is too noisy around, so let me stop here and then continue maybe tomorrow. Thank you very much.